Okay, so today we're going to hit the net ionic equations, the all-important net ionic equations, on a very rainy Friday. So, what a day. I've got some boys having a little party in the back. How's it going, boys? Pretty good? Good. Glad to hear it. But before we can do the actual net ionics, you all need to know your solubility rules. I'm going to condense this list to 3 rules. Okay. Above the board, you can see all the cartoon characters that I have up there. And today you get to meet 3 of them. The first one is Big Daddy. He's a pimp. I heard a yeah. Big Daddy rule supersedes all other rules. And a couple of these are actually combined because they're an always soluble situation. So here we're looking at ionic compounds that are soluble or insoluble in water. Alkali metals, meaning group 1, metal salts, and ammonium, and nitrate and acetate. Those are all I need you to know. I know acetate's written weird there, but all of those combined are always soluble salts, and those make up the Big Daddy rule. So I need you to know those. So this could be written as C2H3O2. In organic, they often write things in order of how the molecules are connected, and so that's a little structural formula as opposed to C2H3O2. So don't worry about it. I'm not going to hold you responsible for it written this way. But anyway, that's Big Daddy rule. So those are always soluble. The only 2 rules I really care about from that point on is Rule 2 and Rule 5, and I've got mnemonics for it, so it's going to be easy to remember. Forget about this. I'm not saying the stuff here that I'm crossing out is not important, but Big Daddy is going to take care of everything else, so you really don't need to worry about those. So I'm taking this list, I'm cutting it down as much as I can. So let's look at number 2. Number 2, what do all these 3 things have in common from the periodic table? What are all those? No. They're halogens, okay? So if you look up above the board, and it's hard for you guys to see because I put a box in the spot, which makes me very sad, but around the corner, there's a little guy named Hal. Hal is kind of a hippie. He's real awkward, and he loves the Aggies. And he's holding an Aggie helmet. So Hal, meaning halogens. Hal, I'm going to go ahead and write out the little rule. Because he's so awkward, he hugs Aggies pretty badly. What this is saying, all halogens are soluble except for, so all halogens are soluble except for Hg, hugs is mercury, silver, and I use pretty badly in the other one as well, and that combines to be lead. So these are my except ones that aren't soluble, so these are my not solubles. So that's one rule. The other rule is for sulfates. And when I say sulfate, I mean sulfate, not sulfide. Okay? So introducing another character named Sol, that is a man's name. Sol there, see him putting an old hag in a bag? That's Sol. He's kind of evil. And he likes to put old hags in bags. So, but he only likes to do them in special areas of the country. Of the world, I mean. So this is probably the worst mnemonic you've ever heard in your life, but no one's ever coming up with anything better, so I'm sticking with it. Sol, can, bag, hags, pretty badly. It gets worse. In Sri Lanka and Argentina. Yeah, Sol. That's an actual men's name if you haven't heard of anyone named Sol. All right, so all sulfates are soluble except, what do you think this is? Calcium, barium, hugs or hags, mercury, pretty badly, lead, Sri Lanka, strontium, and Argentina? No. It's silver again. I couldn't think of a place that was silver with an AG. Angola. Well, that's no different than ARG versus ANG. And Aggie land. Won't you get confused between Hal liking the Aggies then? That might be confusing. Huh? I know, but I like having Hal be the Aggie one. I don't know. If you want to change Argentina to Aggie land, that's cool. I don't think there's very many old hags in College Station, though. Well, maybe, since I am a Longhorn. Whoop, whoop. Longhorns, what? Maybe. All right, so you're just going to have to spend time committing these to memory. It's only 3 of them, so it could be a lot worse. What I want to do now is practice those really quick. I want you to tell me if it's soluble or insoluble and why. One of my favorite things is when I give a quiz and I say, are the following solids soluble or insoluble? And I get yes as answers. So you can just say yes. Silver nitrate, soluble or insoluble? Yes, soluble. Why? Which rule? Big Daddy nitrate. Sodium chloride. Do you really need to think about whether that's soluble? Soluble. Why? Oh, don't say it's salt. All those ionic compounds. Nope. All these are ionic compounds. I'm glad someone kind of said that. These are all ionic. Not all salts are soluble. That's kind of the point of this table. So just because it's a salt doesn't make it soluble. We say it's soluble because of Big Daddy. Okay? Lead 2 bromide. This is insoluble. It's a halogen. Sol can bag hags. Not halogen. Halogen is Hal. Hal hugs Aggies pretty badly. Lead. So all are soluble except for those. Insoluble. Ammonium hydroxide. Soluble because of Big Daddy ammonium. Barium sulfate. Insoluble because Sol can bag. So all sulfates are soluble except for Sol can bag. Calcium hydroxide, and I didn't really talk about it much, and I'm not going to, you can go either way on the AP exam. It's kind of in the middle. We know that strong bases are group 1, and then those bottom 2 on group 2, barium and strontium. Calcium's on the cusp. So I'm okay with you saying either, but the real rule, basically, in dilute solutions, meaning there's not a lot of calcium hydroxide in there, more of it can dissolve. So in dilute solutions, they consider it to be strong. In concentrated solutions, it's considered to be weak. But don't worry, whatever you do on the AP is going to be fine. And I'm not going to give you a problem on tests before that with the weird calcium hydroxide unless I tell you whether it's soluble or not. Lithium carbonate. Soluble because of Big Daddy. Okay. All right, you ready to revisit the evil net ionic equations? They're awesome. No, they're not, but we have to do them. Now, what's going to be big on the AP this year, which has really not, in the past, they really shot for you just giving net ionics, net ionics, net ionics. Now, you're going to be accountable for the molecular equation, which is the first step of what we're about to do, or the total ionic equation, or the net ionic equation. So if you think about how we used to do this on Chem 1, we'd write out the equation, and then we put the state of matter it was. So where do we get the states of matter? If it's an element, we get it from the periodic table, solid, liquid, or gas, right? But if it's an ionic compound, we either have to determine if it's soluble or insoluble in solution. And remember, all our reactions that we're doing in this unit are in water. So if it's soluble in water, what did we write next to it? Who remembers? Aqueous, AQ. If it was insoluble in water, we wrote solid because it was a precipitate or it was something that didn't dissolve. Okay. What about covalent compounds like H2O or CO2? What do you write next to those? Well, CO2, gas. H2O, you'd probably write liquid. Okay, so you just use common sense with the other ones. Whatever state of matter it usually is, that's what you write next to it. And then the last thing we need to think about are the acids and bases. Strong acids and bases and weak acids and bases are all in solution. Okay, so we always write aqueous next to them. But what was different? Who remembers? Strong acids and bases split up 100%. So we always broke those up in the second step. Who remembers what we did with the weak acids and bases? No, this is from last year. We bring them down with aqueous next to it, but we do not dissociate them. So it's the only time in weak acids and bases where we write aqueous next to it, but don't split it into ions in the next step. And we're going to do 2 examples of that here. But let's start with some simple ones first. All right, potassium chloride. I'm assuming you know nomenclature, so I'm not even going to stop. What do I write next to it? It's aqueous because of Big Daddy. Is combined with lead 2 nitrate. Aqueous or not aqueous? Really? Big Daddy nitrate, right? Don't look at the lead and think it's not, okay? Nitrate's part of the Big Daddy rule. These are double replacement reactions, so what 2 things do we make? Good. KNO3 aqueous. Now, lead can be multiple charges, but because it's double replacement, the oxidation state doesn't change. Since it's a +2 here, it's got to be a +2 on the other side. So we get PbCl2. And this is lead chloride. Lead 2 is solid. Halogen, pretty badly. All right, so now we have to balance this. I see I need 2 Cl, so I've got to put a 2 there, but that makes me need 2 Ks. So I put a 2 there, which gives me 2 nitrates, which is good. Yes? Lead chloride is a halide. Hal hates Aggies, or hugs Aggies, pretty badly. Pb. All halogens are soluble except for mercury, silver, and lead. So this is where, memorizing those few rules is necessary. All right, so now we're going to, this is the molecular equation. So if they say write the full molecular equation, this is what they're talking about. Nothing split up. If they say they want the total ionic equation, you're going to do this. You're going to split these up into ions, and you have to take into account the coefficient in front of them. So we get 2 K pluses, aqueous. How many Cl's are in 2 KCl's? 2 Cl minuses. I have 0 sympathy for no charges and no states, and not balanced. Okay, in Chem 1, they might have thrown you a bone here or there. Not anymore. Got to get them every time. How many leads? 1 lead, and it's a 2+ aqueous, plus how many nitrates? 2 NO3 minuses. One of the biggest mistakes people make is they do NO3, 2, and then they do -2. I don't know what's going on. Like, you have to, the subscript is not left there. This totally dissociates, so we have 1 lead and 2 separate nitrate ions floating around. So that gives us K plus aqueous. Oh, this was not balanced. Oh, there's the 2. Sorry, I thought that was part of the arrow. Here's my 2. 2 K plus aqueous plus 2 nitrates aqueous, and I don't touch the lead 2 chloride. I leave it alone because it's solid. Right here, this is the total ionic equation. What if they ask us for the net ionic equation? What do? Cancel what? Everything that's the same. And by the same, it has to be the same in number and the same in charge. So if you had lead solid on one side and lead +2 on the other, you can't cancel those out. Those aren't the same species. They're different states, all right? So what 2 things are the same? Potassium and nitrates. And that is the net ionic equation. Now here's the deal. I'm not going to make you rewrite this, and here's why. On the AP exam, if there's an X and I'm grading it, I am not allowed to know anything about what's under that X. So right now, that is the net ionic equation. But here's the bad news. If you were to be asked for total ionic equation, and you put that, I couldn't give you credit. Because all the ions under those X's, I have to pretend they're not there. All right? So read what it says when it's asking you. What are the things called that you cross out on both sides? There was a word for them. They're just hanging out, looking at each other. Starts with an S. SP. Spectator ions. Very good. You can give Miles a high five. Or is he not in your high five circle? All right. All right. Good to know. All right. Let's go ahead and do another one. Whoa. Silver nitrate and magnesium bromide are mixed. So here we go. AgNO3 is a salt. Is it soluble or insoluble? Soluble, so it's aqueous because of Big Daddy. MgBr2, don't let this trick you. It's a halogen. It's soluble. It's not silver, mercury, or lead. So it is soluble, so we do write aqueous. They're mixed, and what do we get? Uh-oh, what's that? It's insoluble, so it's solid. And MgNO3 2, and that's Big Daddy nitrate. Okay, so we need 2 Brs, 2 Brs, 2 Ags, 2 Ags, and that gave me 2 nitrates. So when I split this up to my total ionic equation, I get 2 Ag plus aqueous plus 2NO3 minus aqueous plus, here's a really good example of what students mess up on. This is so common, and I'm going to write it down. Don't write it down like this because it's wrong. I get this all the time. That's not, A, it's not a diatomic because it's with something. B, that's not how it floats around in solution, and that's not even the right kind of charge. So you need to realize that this splits up into 1 Mg and 2 Br minuses. Gives us, we leave the AgBr2 alone, or AgBr alone, sorry, plus Mg plus 2 aqueous, that's a great AQ, plus 2 nitrate ions. So there's our total ionic equation. Do I have any spectators? Nitrate and magnesium. The trick is to look at the solid. You can't cross out anything that's in that solid, so everything else can cross out. So here, magnesium and nitrate, magnesium and nitrate. And there's my net ionic. It's easier than it was last year, isn't it, after knowing kind of already what to do? Yep, the first year's rough. Okay, we're going to do another one. Then I'll talk about some acid-base ones. Sodium chloride. What is it? In water. That's solid. Yeah? You put that in water, that's solid. Oh, you said soluble? I thought you said solid. I was like, what? Soluble plus lithium sulfate. Oh, not soluble. I'm surprised I don't do that more often. Aqueous. All right, lithium sulfate. Hi. What is it? So it's aqueous. Why? Big Daddy, right? And so we get a double replacement, and we get LiCl, and that is aqueous, and Na2SO4, and that is aqueous, and I have 2 NAs, and then I need 2 Cls, and that makes my lithium as 2. I can tell you right now, I'm done with this problem. I don't even want to do it. Why? When everything is aqueous like that, notice everything becomes spectator ions. So in all actuality, you put those 2 solutions together into a beaker, what happens in the beaker? Nothing. They're already dissolved in 2 liquids, and you put the 2 liquids together visually, unless they're colored. Visually, if you have 2 clear liquids, one with both of those are clear in solution. 2 clear liquids, you mix them together, you get 2 clear liquids in one, and that's still a clear liquid, and absolutely nothing happened. No solid came out, no nothing. And the other ones, we had silver chloride dropping out and all the different solids coming out. So this, in my opinion, is a no reaction. This is the only kind of no reaction you're going to run into. We're not going to give you, I don't know if you remember the single replacement reactions where you had to utilize that activity series to see if one was strong enough to boot out the other. We're not doing that. Okay. So all our reactions that are non-this will react. Now, if they ask you for total ionic, though, you still need to split all these up. But we're not going to do it today. Okay? All right, acid-base. We're going to do 2 of those real quick, and then we're done. Now, the only thing that's confusing about acid-base is when you split up and when you don't. It's not hard. Weak acids or bases, you write aqueous, but don't split them. Strong acids or bases, you write aqueous and split them. So sodium hydroxide, I like to classify my acids and bases while I'm doing this. Sodium hydroxide is a strong base, and it's aqueous. What about phosphoric acid? Weak acid, and it is also aqueous. If you get a bottle of phosphoric acid, it is in a solution. It's in water, and there's no weird solids or anything floating around. It is aqueous. Not all of it dissociates. Most of it exists in the H3PO4 form, so we leave it alone. And so we're going to do a double replacement reaction, and what are we going to get? We'll balance it in a second. This is what you get for any neutralization reaction or acid-base reaction. We always get an acid and a base makes water and a salt all the time. So what is the ionic compound we make? Na3PO4. When you're balancing these, it's actually a little helpful to think of water as HOH when you're balancing, and so you can just balance OHs with the sodium hydroxide. But I see I need 3 sodiums there. So that makes me need 3 waters, because I'm 3 hydroxides. And because I'm going to think of water as HOH, I need 3 waters to get 3 OHs there. And then that leaves me with 3 H's, 1 phosphate, 1 phosphate. And that's balanced. So what would water state be? Liquid and sodium phosphate. It's a salt. Is it soluble? Yes. Yes, Grant, do you have a question? Okay. All right. So let's go ahead and break up what we can. This is a strong base, so we get 3 sodium aqueous ions plus 3 hydroxide ions, aqueous. What do I do with H3PO4? Leave it alone, and we write it like this. And then we get, what do I do with the water? Leave it as a liquid. And then I get 3 Na plus aqueuses plus PO4 minus 3 aqueous. Do I have any spectators in this? Not very many, but what are they? Yes, Charlie. It's weak. So classify your acids or bases as strong or weak. If it's weak, we still write aqueous, but we don't split it up. No, I just forgot. Was that your question? All right. This one I'm going to change, and I'm going to just make it, because we already did a weak acid one, I'm going to make this a strong acid. I'm going to make this a strong acid, strong base reaction, hydrochloric acid. Okay. HCl, we know, is a strong acid, so what do we write? Aqueous. Potassium hydroxide, strong base, so it is aqueous. Double replacement reaction, every acid and base reaction makes a water and a salt. Liquid, water, and what salt do we make here? KCl, aqueous. I really like the strong-strong situation. H plus aqueous plus Cl minus aqueous plus K plus aqueous plus OH minus aqueous gives me H2O liquid plus K plus aqueous plus Cl minus aqueous. So what do we cancel out? Chlorine, potassium, potassium, chlorine. I want you to look at this. This is why we call acid-base reactions neutralization reactions. I need you to realize that this is the net ionic for every single combination of strong acids and bases in the whole wide world. I can mix any strong acid and base, and this will be my net ionic. I don't care what it is. Net ionic for all strong acid, strong base. So I'll tell you this. If I just outright ask you for what's the net ionic for this equation, I'm okay with you not showing work. I'm okay with you recognizing it's a strong acid and a strong base, and bam, just writing that out. I have no problem with that. Do y'all see why every single strong acid or base would have the same reaction? Okay, so that wasn't as painful as last year, hopefully. You have a brand new calendar that I need you guys to download. I had to do a lot of rearranging because of the whole junior going to the college fair, and then we have a late arrival day, and I need to do some rearranging. So please replace your old calendar with the new one. And then you have a bullet lab due Monday, and your homework C. Thank you. All right, go ahead and clear off your desk. Get your calculators out for your quiz.